This is Ritesh Srinivasan and welcome to my channel. In this video, I'll explain about an interesting approach of combining free text radiology reports and images to generate better representations or visual features on the radiology images, specifically X-ray images. So I stumbled upon this interesting news in this site, which is Science Daily, and under artificial intelligence, I stumbled upon this interesting news which talks about an engineering team developing new AI algorithms for high accuracy and cost-effective medical image diagnostics. So then I went into the article, and from the article I landed up on this particular Nature paper. Okay. So what is this paper about? So, with the advent of deep convolution neural networks, medical image analysis has achieved tremendous progress, a lot of breakthroughs, right? But for this, what do you require? You require a deep learning model, right, or a convolution neural network, which has been trained on some other large scale data set like ImageNet, and then transfer learning is done on the medical images, right? Specifically over here, they are talking about X-ray images or radiographs. Okay, radiographs here refer to X-ray images. So this is the normal way of doing it. Okay, there is also self-supervised learning like contrastive learning, which is being used now to get better radiograph representations or X-ray representations. Okay, but what is the problem over here? There is domain shift from say natural images to medical images when you are doing transfer learning with a convolution neural network. And the pixel intensity distributions are different in your X-ray images when compared to say the ImageNet images, right? And if you look at self-supervised learning, what they claim over here is that the performance gaps are still there. So what is the need of the hour? You need to build large-scale annotated radiograph datasets for label supervised pre-training, right? You need large-scale annotated X-ray images. Okay. So what these researchers from University of Hong Kong and the other University of Xiamen University, China, what they have proposed is a framework called REFERS, right? This particular model makes use of supervision signals from original radiology reports accompanying radiographs. So whenever a chest X-ray or some kind of an X-ray image is generated, a radiologist sits and looks at the image and a report is also generated. So now you have the report. So earlier what they used to do is that it used to be a two-step process, right, to generate these annotations. First, what they will do is that a radiologist will look into the image as part of their clinical routine or the X-ray image. Then they'll create a radiology report. In the second stage, there will be a human annotator who will extract and confirm the structured labels. So what is the disadvantages? This is time consuming. And if mistakes happen somewhere in this process, the mistakes gets carried forward, right? So that is where these people have proposed something called as REFERS, which is reviewing free text reports for supervision to directly learn radiograph representations from accompanying free text radiology reports. So how do you combine the text reports with the images to generate better image features, which you can use for downstream tasks like image classification, lesion identification, and things like that on these X-rays. Okay, so here is their architecture, right? This is the whole architecture. So what they do is that for every patient study, say for example for a patient, they consider 3 views. So here is a chest X-ray, so they are considering 3 views. Then they have something called as a radiograph transformer, which is an image transformer. Okay, so this will generate some image features, right? Or the image basically a representation out of this radiograph transformer. They are then concatenated using something called as attention for view fusion. Okay, and then that is given as an input with the ground truth radiology report to something called as a report transformer for generating report. Okay, in this process of using the radiology report over here plus this image features, right, they are training a report transformer to generate a report. Okay, so I'll come into the details of this particular model over here. So this is the basically your image transformer to which you give an X-ray image. So this is your standard image transformer, where you give patches of this your input image. It does some kind of transformations on that, and basically you get some features output over here, right? What they do is that for each such view, they concatenate the view and then pass it to another neural network, right? They also do some kind of softmax weighting over this attention. They do an attention network over here and get image level features for each of these views, okay? Basically from this transformer output, that is what this is. They get image level views and then that is concatenated to get a image level representation for a study. Okay, so basically these three images are kind of fused over here in this representation, right? But each of the image is sent to the radiograph transformer. You get features on which you do attention for view fusion, that is this particular network, and you get a image representation, right? Now what do they do over here? So this is where the interesting part comes, right? So now you have an image level representation for a particular image, right? Particular set of images for a particular patient. So that is VK, okay? So K stands for the kth patient study and V is the visual features, okay? Here you have the ground truth text features, okay? You have the ground truth text, basically ground truth radiology report, okay? So what is done over here is that radiology report of the kth patient study is over here. Like that you have up to B, K plus B, where B is the batch size. Similarly, visual features over here for that batch, okay, where B is the batch size during the pre-training stage, okay. Now this is fed into something called as a report transformer, which generates a report for each of these visual features. Basically for each study, it generates a report. You have the ground truth report, right? So with the ground truth report, you can have a task language modeling loss, okay, whereby this transformer will get trained to generate better reports. This is one contrastive learning or one kind of a loss, a language modeling loss between the visual features of a study and the ground truth report, right? Using the visual features, you generate a report, basically report tokens, and this is one language modeling loss. The other loss over here is a contrastive alignment loss, which is basically you have the text, okay. Basically what is done over here is that the report is fed into a BERT transformer and you get some tokens from the BERT transformer, okay. So these tokens, basically there is a contrastive loss calculated between these tokens and the visual features, okay. Now the total loss for the network is a combination of this language modeling loss and this task, basically the contrast alignment loss between the image features and the report, which is being the tokens of the report generated using a language transformer over here, okay. In this way what happens is that when you train a network over here in this way end to end, what happens is that you get very good image level representation features. So the image level representation features are supervised by the text report. So that is the combination which is achieved over here. I find this as a very clever idea of using the ground truth, okay, which is already available, and skipping the human annotation phase, right? Whereby if you have a large number of X-ray images corresponding their radiology reports, you can train this network to actually get better image level features. So that is what is claimed over here. So the two losses over here are, one is like you take the image features and you compare it with the generated text features from a language transformer which takes your report as input, right? You also give these image features to a report transformer which generates reports, and you do a language modeling loss with the ground truth report. So you are using the ground truth text report to actually drive this report transformer to generate better reports. At the same time, you are also trying to align the image features with the text over here. So that is what is achieved in this particular paper, and they claim that this kind of method gives very good representations which are more transferable representation for downstream tasks, okay. And they say they have achieved some very good results over here on these X-ray images. They say 9% improvement on a certain condition, okay, 7% improvement were achieved over 2 common lung diseases. So that is what is explained over here. Okay, so in this section they explain about this view fusion module and how this combination is done, right? How this network is this. So let's look at some of their results where they claim, let's go to the results. So these are the set of results, right, where they have the ground truth annotation done by human, and this is the over the attention map, over the visual features attention map, right? This is where they highlight that this fuchsia color is where maximum attention is shown. So if you look at this, this kind of actually shows correlation with this human annotation, right? In all these images, in all these X-ray images, that is what it shows, right? So what they are saying is sample visualization of 12 randomly chosen images, and for each sample they represent the original image on the left with the basically the annotations by humans and an annotation map generated from refers. Red boxes denote lesions annotated by radiologists. Attention maps, the fuchsia color attention represents attention values generated from this algorithm refers. Darker the color, higher the confidence of a specific disease. Green boxes are our predicted lesion areas generated by applying a fixed confidence to the attention maps. So when I applied a fixed confidence, this is the green bounding box which has been generated. Okay. So the whole idea of this kind of a network is to actually combine the ground truth text which is available along with the images, medical images, basically X-ray images, to actually to get better features from these medical images and also kind of annotate the medical images. And when you do this over a large data set, you get a nice pre-trained data set for your downstream tasks. The downstream task could be lesion identification, could be classification of these images based on various diseases. So you get very good image level features. Okay. I hope you find this video on how to combine text plus images in the medical domain, specifically with respect to X-rays, to get better features from the medical images useful. I know this is a very short video to explain all the details of this paper. So what I'll do is that I'll put a link to this paper in the description of the video. If you like the video, please like, share, subscribe to the channel. See you in another video. Happy learning.